All right, so here's a fun problem to work on the board. So 4 states, state 1 counts in this funny gray code 0001, 1110, and back to 00. If your input is a 1, it counts. Anytime your input is a 0, it takes you back to state 00. So 00 is going to be a popular next state in your table. So, about 20 people. So let's do groups of 4 and pick a spot on the board. We can do 2 or 3 groups in the back and 2 or 3 groups up here. So groups of 3 or 4, and leave yourself lots of space, right, for your table and then somewhere to do some of your scratch work and so on. And so let's first try to implement this with D flip-flops. And start working systematically and ask questions, and I'll walk around and see how and what you're doing. And this will be a really uninteresting video to watch.
We're just validating something different. Okay, now we can. All right. We have 4 stages and 1 I'll start using the presentation. 3, 4, all right, okay. We put that. And I feel like there's just yeah. Oh yeah, yeah, okay. Okay, states in there. Okay, just 0. Okay. Okay, like
so next
tricky.
Oh yeah, we have to do the Q1 and Q1 and Q0. Yeah.
Before you go on, double check those 2.
Oh, S01 goes to S11, and then S10 goes to S0.
Yeah, good.
1 0
goes, when it's a 1, it goes to S11. And then S10 goes to S00. S11 goes to S1 next. And yeah. So.
Oh wait, how did we determine that again? By looking at that thing.
Go ahead and put down your Q values that correspond to this.
And then 0 0
0 it goes to S00.
Is that N not good enough?
1 0 goes to S00.
We have S00. It's pretty much the same.
Yeah, that's what we're doing too.
Let's do the same way that you did.
And then S11 0. And then we have to do that's just like a reason.
Next
Z values. It's all 0s except for S11. S11. 0 1 1 1. This is yeah, this is the next one, yeah.
Cool, good.
After that, we have to to do inputs, and we're doing two swaps. So it's going to be D1 and D0.
All right, so is this the present Q1, Q0, or the next Q1, Q0?
This is next.
Okay, so label it next.
And then it's the
Q1
same
plus
as the
Q0
input, right?
plus.
So it's a
Yeah.
Q is next
Present
to
state
zero.
input.
So,
Next thing?
Yeah.
I'll have
That would be what we want to do.
So,
So, yeah, because so if we want to get the 0 to 0, we have to do 0. And then we
so
have to
for
do 0
present
to
state,
0.
you need a Q1, Q0 column.
0 to
For
0.
next state, you need a Q1 plus Q0 plus column.
and the definition is just one.
And they're gonna be the same, as they're gonna be based on what the actual state
Is
is.
that
And it doesn't make any difference.
Yeah.
We're trying to get these all to zero.
Oh, now I have to, now this.
Oh yeah, I totally forgot. Yeah. I totally forgot. For some reason I thought and then that was different. Okay. Cool. And then after that is because we have the inputs, which is D1, D0. We have the inputs of the two flip-flops, and we have the input of the X. And yeah, that's it. And then for the output, it's just going to be NS, right? NS and then that's also that's the next state. And this is going to be
And then S1, 0, 0, 0, and 1 on S1. I think we need.
Okay, so let's call this part A, and then B is just with the T, so we'll call this
Just
T1.
directed, but S1 is 0.
T1.
It's current.
That's how like,
It goes
I totally forgot how to
Current
do
state
that.
is next.
Zero,
One on S1.
Oh, you switches it together? Oh, okay. And so for this one, when it all just be
All right, your D's look perfect.
We're looking here.
Very good.
What value of
and so
T1
T is
So we don't want to toggle
yes, so it's 0. But this
that
one we
one we
want
want to toggle.
because we want to get these to 0, right?
That
Okay,
one
so
we
this will be
want to
1, 0, this will be 1, 1,
1, D0.
Okay. And then these ones are and then this will be just 1. This will be because we're getting 0, 0.
Yeah, and then
So before you do it, C is J. So we're going to do J1, K1, or yeah, J1, K1.
yeah.
And then we need.
And then when it's 0, 0, it doesn't change. So we're going from
We can use butters.
oh yeah, and dashes. So from this to this, it's going to be we want both of them to be 0. All right, let's look. Oh yeah, let's get these two. So let's look at.
He wants to do it.
Oh yeah.
Wait.
I'll make sure. I'll make so we know
Q1.
Q1. Do the Q1s first.
Never goes in. But the next state is what? 0, 0? Oh, it's gonna be.
Yeah, yes, is 0, 1. And oh, next question. Alright, so look at Q1 first. Q1 or it'll be 0. So it's going to be 0. So it's going to be 0 bar. Or 0 dash.
Take the.
And then from this one, it's going to also
Figure out how to make it.
And then from 1 to 0, that's also it would be
Would be inverse one, so
Bottom.
yeah, when that. And then from 1 to 0, same thing. And then from this one 0 to 0 would be 0 to 0 to 1. We haven't done that yet. So 0 to 1, that's going to be that'll be inverse or a 1 0. So that's going to be a 1 dash.
It's okay.
Figure out if he needs to be 0.
From 0 to from 1 to 0 is going to be dash.
dash is
So 0 to 1, and then 1 to 0, then 1 to 1, that's The dash zero, yeah.
Zero. And the next would be 1 to 0. So that would be.
No, yeah, wait, because we're doing the second part. So it's gonna be 0, 0. That's gonna be the same as 0. And then 1 to 0, we did that. 1 to 0 is 1, 0. Oh, no, it's dash 1. And then 0 to 0 is 0 dash. And then 1 to 0 is 1, which is dash 1. And then 0 to 1. 0 to 1 is 1 dash. And then 1 to 1, that is. Oh yeah, we did it here. And that's going to be dash 0. And the next one is 0, 0, which is 0 dash. And then 1 to 1 is dash 0. Is it dash 0? It's dash 0, yeah.
So she
That's it, right?
now it's she wanted to.
Oh yeah, we should probably should we? There's a lot of equations for three like different groups of flip flops. Yeah, I guess we could. We got the. I don't know. We'll see how much else we have. Yeah, because if we get started on it, then that'd be it. We wouldn't be able to finish it. But yeah, it looks good though, right? Because we got all the dashes in, and then we can do. Yeah.
That's the one.
There's a randomly cut out.
I mean, you guys know.
I guess we just think about what the gates would look like, or I think about like the terms would look like, the product. No, yeah, especially with that all zeros, it would be for the top part where x is 0, all that is just 0. So if you do five times, so let's simplify. We just simplify it how we did it before. So we'll do
We're looking at
yes, Q1.
the only thing we're moving.
We're just getting rid of these two. And then
This may not change. Okay, so are you gonna do like the first, second one to be actual? Just, are you gonna do A1, are you gonna do it all? I mean, the actual is Q1. Are you gonna do like a 1 step? Don't care.
Yeah, that's
Actually.
When we look at present,
Okay, so, yeah, only present 0.
0 to 0.
It would be 0, 1, or 0 down here. Yes, same.
wait, you're trying to get Q1.
1 to 0, that would be 4, that would be 0, 1, that would be 0, 0.
The one dash.
Just super methodical, just like figuring everything out.
Yeah.
And then just like
That's true.
doing it.
Dash is proof.
I think we're using the right one.
Yeah, so 0, 1, dash, 1.
But we don't have one. Because we're only looking for one.
Okay, now we'll get to 1 to 0. I think it's the same thing. And then 0 to 1.
All the zero.
And I think 0 to
That'd be one dash.
1 to 0 is we haven't done this one yet. Oh wait, we should have gone through each one. No. Number 2. That's way too old. So to get to 1 to 1, it would just be
1 would be
0, 0. Or 0. Or 1 to 1. Don't care. 0.
And next would be 1 to 1.
1 to 1.
Would be 1 basically perfectly rounded. 0 to 0.
Yeah, all the options. What do you think would be the easiest one to do? Default keyholes or JK? Like just like the amount of total amount of components you need. But also think about this one from the whole top section. Yeah, I feel like the default box is like you have the whole 4 like
0, 1.
whole areas where you don't even have to worry about
Dash 1.
simplifying because it's just all zeros.
These two. First one has 0. Second one.
And 1 is all
It switches from 0 to 1. 1 to 0.
You got some extra time, you can go ahead and do some of the formulas. It makes it easier to compare, but.
We have to do D1 first, right? And we have to do D0.
You can move the screen.
Yeah.
Yeah.
Zero, one. We need 3 boards. We need it's
Right.
Where there's all zero. I know it's all zeros. What would the I know we use max?
It would just be
like what would that max range? Would it just like because everything would just be don't care, so it just
I
would it even matter?
You're just going to start doing these, and you can do like X and do the case of is there something to do with 0?
So it's going to be X, because these are the oh yeah, these are going to be the inputs, so it's going to be the output.
We can just do
And then it would just be 0 bar, it would just be 0 bar, or D1 bar. It'd be this one we don't care. You'd make this.
We're trying to get to 1, 0. 1 to 0, yeah.
So would it be Q1 bar? No, it'd be Q1 and Q0 bar.
Yeah.
And that would be the entire.
You're running it from now. Yes.
Probably the easiest thing is one max. You guys probably like we have that max. We're using product of sums.
So it would be yeah.
Wait. So this is
So this is some.
0 to
You have to make all of those
1, 0. Wait, don't do it yet. No, this is Fourth one. Wait, did we like mix
I can push it down.
One sec. Can you double check one value on here?
1 to 0 now.
Your very last value, that last 0 for K0, bottom row. Double check that.
Oh, it would be
0, 1 or 1, 1.
because we're trying to get the 1 to a 0. So 1 to a 0 would be this one. Or
Yeah, don't care.
so yeah, it'd be straight. So it wouldn't be 1 dash, it'd be dash 1. Because it's this one and this one. So it's 1 to 0. Because we're trying to get it to 0. So it'd be 0, 1 or 1, 1. And then so it'd be dash 1. So you swap those around.
1, don't care.
I think we
One, don't
Okay,
care.
that looks perfect.
So on the homework here, normally they give us the state line or key, right?
Yes.
Oh, okay.
Yeah, because it explains what the diagram is saying.
Sorry.
Alright, homework.
I was thinking homework is a good idea just to take the paper and turn it sideways.
Yeah.
And then do a tweet with that.
Totally.
Because I was looking at your the way that you wanted to organize our homework,
Mhm.
and I've always been where it's just, right side up instead of sideways.
Right.
So I don't want to like.
I should mention that to the class. So yeah, you can do that, but only do one page with one table on it. Don't write formula sideways and things like that, right? Just do that on one page by itself, nothing else on that page except the heading.
Okay.
Right? And then if you have formulas and equations and stuff, just continue that on the next page and the third page.
So I could draw two tables on the side, but still leave the name and the information on the
Yeah,
top.
yeah.
Not the top of the side, but the top right side.
The usual top, yeah. Name, page number, all that. Yeah.
And how many questions what do you expect? Is it like question 1, then do all this, but
Oh yeah, okay. I don't know why I was. Yeah, because we were looking at this. Okay. Yeah, I don't know why I was looking at the zeros and how to work.
What would it be other than one ABC, two
Yeah, and it would
ABC?
be math.
Usually if they're ABC, it's a state diagram and A is like E flip flop, B is like T flip flop.
You want to do the circuits for this?
Okay.
It's usually one per problem.
Like,
Oh, you looked at homework yet?
I have not.
I think it's 7 questions.
7.
We'll run through the homework really quickly just because I want to make a few comments on it. And I want to talk about the format. Can you slide that board back a minute? I wanted to see one more thing on there. Okay, so
Don't care means it could be either 0 or 1.
I'm wondering about the first dash 0. No, 2 down. Yeah, that one. What's the previous current value? Q1. So this is a 1, 0. Okay, so
Alright, so the first for D1.
What do we put in there?
At least for this one.
So one,
Oh yeah, we
zero,
did.
third one.
Oh yeah, yeah.
Which one?
You're going from a 1 to a 0, so you have to be a 0.
D1 will so it's just going to be X Q1
Dash
Q1
1.
bar.
Yeah, it should be dash 1.
And then Q1 bar. And then Q0.
Okay, so how's everyone feeling about this? Pretty confident you got the idea?
Yeah,
Maybe?
Yeah, it just takes time, just like time to think through it. And you might have like.
So from eyeballing tables, it looks like everybody's got the same values for the flip-flop inputs, which is a really good sign. Because they match for that, I think you should have. So I think you got the process down. And it's independent of what the state diagram is, right? Their numbers are going to change, but it's exactly the same process, right? It's just how many flip-flops you have, what kind of flip-flops, and how you fill in next state and present state and inputs. So making sense? All right. So you can go ahead and sit back down. Let me make a few general comments about this and talk a bit about the homework and some other stuff. I'll leave it up for a while. I'll let the 223 class stare at it. All right, so this business of if you've got 4 states, you could have 4 flip-flops. Right, and we could say that any other combination of these flip-flops is an invalid state. We don't care what happens there, right? This is something that's done sometimes. This is called one-hot encoding. Hot usually means a 1, a bit that's turned on, that's an active, that has voltage, that is somehow present. So exactly one of our state variables is active, right, or is equal to 1 at all times, right, and only 1. And the nice thing about one-hot encoding is if we have a situation where we're moving from, say, state B to state C, eventually, right, this bit's going to go off, and this bit might go off before this bit comes on, or this might come on before this bit goes off. But if this bit Q2 turns on temporarily, we're going to go from this state to this state, and then eventually to this state. This is an invalid state. We're not going to do anything in that state, right? No matter when the bits actually transition. And if this second bit changes first, we'll end up in a state like that, and then this first bit changes, and we end up in our correct state, right? And again, if this bit changes first, we'll go from here to this, and then go into our final state. And this is also a state where we don't do anything. So one-hot encoding is a way to deal with potential glitches, because the intermediate states that you might hit in going from one state to the next are listed as states where we don't do anything. Now, if we use full encoding, which is what we've been using, it's the usual very different situation. Because if we're going from, say, state B to state C, state B, our flip-flops look like this. Well, if this Q1 changes first, before Q2 changes, right, we started in B, eventually we ended up in state C, but in between we went into a valid state D, and D might be the emergency shutdown state. And even if we're only in this state for a few nanoseconds, that might be enough to trigger whatever activities happen from state D, and we could have unexpected effects. So one-hot encoding helps us manage this possibility of timing-related glitches, and so you see it used sometime. All right. What else do I want to say about this? That's pretty much it, other than once you can make state machines, you can make anything. Right? They're really kind of, they're the key to all the other design we might want to do. All right, so let's take a quick look at the homework. which I posted last night. So question 1, design a 2-bit binary down counter. Okay, 2 bits, so it counts 1 1 1 0 0 1 0 0 and then goes back to 1 1. Okay, so 4 states, and the output in each state is just, the numbers 3 2 1 0. And this is one of these: use D's, use T's, use JK's. So, I gave you all these draconian rules for formatting your homework. So, staple goes in the corner, and I don't even remember my rules, but it was something along the lines of name and some other stuff, and then page number, 3 out of 245 or whatever. No. And then I said, sequential, and in the left column you put question number and so on and so forth. Okay, so these tables get really wide. Okay, so this is the one exception where I'm going to let you flip your page to make these truth tables, but I want you to do the following. Keep to your name on the top here, right, stapled in the usual place, and if you're doing question, let's say we're doing question 1, you're going to use one table for all 3 of these. Okay, so you can label this 1A, comma B, comma C. Okay, and then flip it over and make your table like this. But don't put anything else on this page. Okay, if you're writing the equations that correspond to your table, right, put that on the next page. Okay, don't squeeze them in here so that I have to keep flipping it back and forth and so on. So you can flip sideways if you want to make a wide table, but make sure that's the only thing on the page. And you can do one table for all the different parts if that works for the problem, like with question 1. But if you've got stuff to do before this, put it on a page before. If you've got stuff to do after this, put it on a page after. Does that make sense? I'm not going to be like super duper picky about it, but I don't want to throw out everything that you've been doing on the homeworks, because the homeworks have been amazing. But this one, I'll let you make wider tables because it'll help. All right, question 2, no big surprise here. Design a binary counter that counts from 2 to 7 and then resets to 2. 2 3 4 5 6 7, 2 3 4 5 6 7. You don't have to know anything about counters to do this. All you got to do is build a state machine. So it's going to have 6 states, and the first state should output 2, next should output 3, and then 4, 5, 6, 7, and the last state should go back to the first state. So that's how we translate that description into a state diagram. Right, so draw a state diagram, list what the outputs are in each state, and then again, 3 parts, 3 types of flip-flops. Okay, 3 is phrased a little differently. Synchronous finite state machine, that's all we've been talking about, is synchronous. There's a clock and they're finite state machines because there's a finite number of states. And basically this machine has 2 states, and it has 2 inputs, X and Y, and so if your input is 0, 0, and you're in A, your next state is A. If your input's 0, 1, you're in A, your next state is B, and so on. So this is a different version of a state transition table. Present state, and then there's 4 columns for the inputs, and there's an output. But you can turn that into a state diagram, or you can build your state transition table from this, right? We just list X and Y as columns, and we'd end up with 8 rows. And then there's basically a next state and an output for each of those. Okay, so part A, derive the minimum excitation and output equations for a full encoding design using T flip-flops. So excitation equations, those are the inputs to the flip-flops, right? That's T equals, right? And there's only one flip-flop, so it's just T0 equals blah, blah, blah. Part B, same thing, but you're using one-hot encoding. So 2 states, 2 flip-flops, T0, T1. And the excitation equations are T0 equals blah, 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 T1 equals blah. And then the output Z equals whatever. Okay, and then show the implementation, so sketch the circuit that goes along with that. I don't think you have to do implementation for 1 and 2. If it just says design a binary counter, you can take it as far as equations. Okay, and you don't have to actually sketch it. But this one says show the implementation, so go ahead and sketch it. All right, question 4, finite state machine, D flip-flops, rising edge triggered, illegal state should go to A. So basically you want to move from state A to state B to state C and back to A. And if you use 2 flip-flops, you're going to have a 4th state. If you're in the 4th state, you should go to state A for your next stage. And then there's 2 outputs generated, Y1, Y2, and another output RCO. Okay, and again, take that as far as equations. Five is the happy sad machine, so JK flip-flops design a circuit. So let me write these down. And I will post these in the homework. So 1 is just equations. 2 is going to be equations. 3 is going to be a circuit. Four is going to be equations. Okay, so 5, let's do a circuit. And then 6 is a weird one. If you try to do 6, you're going to end up with a huge state diagram, and I don't want that to happen. So 6, you're designing a locking system with 8 keys. Okay, 0, 1, 2, 3, 4, 5, 6, and a star. And it's normally locked, and it unlocks only if you hit star 2, 3, 6. And entering any other sequence locks the system. So let's design this so that any time you hit star 2, 3, 6, it unlocks. Okay, and if you hit 0, 0, 0, star 2, 3, 6, that should unlock after that 6. If you hit star 2, 3, 5, and then hit star 2, 3, 6, it should unlock after the 6. So it doesn't get permanently locked if you type the wrong thing. Okay, but anytime that you hit star followed by 2 and then 3 and then 6, it should unlock. And once it's unlocked, it stays unlocked. Okay. And since we have 8 keys, we have 8 inputs, and you're probably going to need 4 states for this, and that's going to be a big diagram. And so for this one, I'm going to say just do the state diagram. So you don't have to do the table, you don't have to come up with equations, you don't have to come up with a circuit. Okay, just do the state diagram. And if you want to take reasonable shortcuts, meaning that on your transitions, you could have, 1, 3, 4, 5, or 6. You can do that. As opposed to having an arrow that's a 1, an arrow that's a 3. So if you have multiple arrows that are going to the same place, you can go ahead and put those all on 1. Okay, just make this thing reasonable sized. So this one, the real goal is to sort of think about the state diagram, come up with a nice clean diagram description of this behavior. And then 7 is 7, let's do a circuit. And it just counts 3 bits in that order, what we call gray code. So I'll post these notes on the homework, like in the next hour probably, just to remind you. But 1 and 2 equations, 3 a circuit, 4 equation, 5 a circuit, 6 just a state diagram with abbreviations allowed, and 7 is a circuit. And I'll type those up. That question?
So like, what would the key for the first problem be? Or do we have to figure that out?
You're drawing a state diagram, so it can be whatever you decide.
Okay.
But it's probably going to be a Moore machine, right? So you'll have a state, line and then an output specified, and then if you don't have an input, you don't need to have an input. It might just change from one clock tick to the next, so you don't have to have an input. All right, so 2 minutes left. So here's the traffic intersection test bed, and it's very professionally made, right? This was when I had lots of free time. But it's got the T intersection, it's got the traffic light, and there's red, yellow, and green LEDs on each of the 3 lanes. There's a little bubble here, there's a magnetic sensor underneath, and we have 3 cars. We have a Pagini, it's a cool car, whatever it is. And we have this one, and then of course we have a school bus, and they have magnets inside which will trip these sensors, and all of the sensor outputs and the inputs to the LEDs are fed into this little proto board. Okay, so if you have your circuit and your circuit is working with switches for the inputs and LEDs for the outputs, we can take that and we can, instead of going to the LEDs, we can go to some of the spots on here, and instead of reading from the switches, we can read from other spots here. And you can basically hook your circuit up to this test bed, and then, you know, if a car comes up here, it should get a green light, and if a car with higher priority comes along, that should turn yellow and then turn red, and this should turn green. And your circuit basically controls this, right? And this is just sort of the brainless output device, and your circuit is the brains that drive it. So if you finish your lab and you want to play around with this, right, let me know and I can help you hook it up. And it's kind of more fun than flipping switches and watching LEDs on a board. So that's an option. All right, so work on the homework, keep working on the lab, bring homework questions on Tuesday. We'll dig more into synthesis, and then we're going to switch to our last subject of the course, which is Verilog and programmable devices.